Okay, so we're about to start. It's already time. Hi everyone, thanks for coming today. My name is Danil Zburivsky. I work at the MySQL DBA at the Pythian group. And today we are going to talk about how we build the continual replication sync process. Before we start, I'd like to tell a couple of words about what Pythian is and what we do there. We are like global leader in the remote database administration and management. So we support production systems for more than 150 companies all over the world, such as Forbes, Sports, Western Union, and others. We support MySQL, Oracle, and Microsoft SQL databases. We also provide 24/7 support for these production systems, system administration, and some special projects as well. So, let's start with our topic. A lot of MySQL installations and systems heavily rely on replication for different purposes. I think if you are managing some production environment, or if you are working with MySQL installation, in most cases you will have replication involved. So you will probably have one master and slave, or many slaves, depends on what your needs are. But the fact is that a lot of people heavily rely on replication for different purposes, for backups, for reporting, for sharding, as we heard a lot of on this conference. But the problem is replication is not reliable. And the way it was built in MySQL, it still has some flaws in it. And it's very easy to break. And the worst thing we found about replication, and I think you also found that it can fail silently. I mean, you think that replication keeps going, things keep updated, but the problem is you get the different data on the slave than the data is on the master. And that's a critical problem, because like, if you rely on the slaves for backups, you can be sure whether your backups are the same, have the same data as you need. If your master dies and you will store it from the backup, you may be very surprised with this fact, like some orders missing, or some users are missing, or some data is not the same as you expect it to be. Why this happens? So the basic thing is there are several ways replication can fail. So first of all, it can be the non-deterministic queries, which produce different results on master and slave. For example, if you rely on some functions like sysdate and don't use that sysdate is now option in MySQL, this date will produce actually different results on the slave and master. So when statement arrives to the slave, it will give you a different date because this function is non-deterministic. It doesn't produce the same result all over again. Another thing we faced quite often is the wrong initial replication setup. So it turns out when you're setting replication, some people miss the parameters. They start from the wrong position. They start from the wrong binary log, and so replication starts flowing, but the data gets out of sync. And the problem here is actually even one small update in the table can with time grow to many changes that will happen on slave, or that will happen on master, for example, and will not happen on slave. For example, if one row wasn't updated on the slave, and then there are queries that are relying on this field, for example, on this value, they will keep updating in the while replication flows, and data will be changing in a different way on the slave than it changes on the master. So with time, you may get very different results on the slave. The slave crashes. If the slave dies badly, I mean, for example, the hardware crash, or like MySQL dies unexpectedly, there's a big chance that data in the master info file won't get updated with the right position. So when you restart replication, you may start seeing the duplicate keys, because it's pulling data from a bit behind than it should be. And of course, the human factor. We often see the problem, not very often, but we sometimes see the problem with our clients, where due to the human mistake, people start updating their slaves instead of updating their masters. Yeah, not all of them have the read-only option enabled, and that's what that's like a good fix for this. But again, not in all cases it's so. And especially if you are using slave for failover, for example, if you write to your master and then you need to fail over to your slave, you do updates on the slave. Sometimes application configuration files don't get updated, and some of the application nodes still keep trying to write to the slave, and they still trying to update the slave instead of the master. So that's why we need to make sure that your slave has the same data as your master does. And I think you all understand that how critical and how important this is. So there are some different ways to do this. The easiest and it's not actually very applicable in production. I mean, you can do just you can dump some tables you want to share. You want to order them like in a primary key order, and just compare using, for example, a diff or any kind of tool set you come up with. Just see if there's any data difference. But that doesn't work on any significant amount of data. I mean, you can't just log a table master while data going, and again, if you have huge data sets, this will not work because it's too slow, it consumes too many resources, so this will not go. For the MySQL tables, there's a way to run the checksum table statement. It's very fast on the MySQL because it had a built-in checksums, but again, it's only limited to MySQL. And the final way, which we are going to talk about today, is using the mk-table-checksum script from the great toolset called MartKit. Can I ask you how many of you have used the mk-table-checksum script already? Okay, many of you. So I will give the basic ideas of how it works for those who haven't used that, and we will then go to the how we build the continual process for this. So this is a slide about where can you get the mk-table-checksum script. You can go to the MartKit project page, you can download it from the Google code, you can use the wget to download it. I want to warn you that sometimes the last ways don't always get you the latest version of the script. We faced it several times. So just keep in mind and compare your versions to what is updated, because it's still in development, it still gets bugs fixed, so you should be tracking what version do you have with what is the latest one. So mk-table-checksum, how it works. Basically, there are two ways of comparing the data in different sources. So basically, it was developed to compare data in different sources. And by different sources, I mean not only master and slave, but you want to be able to compare one table in one database against one table in another database on the one machine, and so without relying on the replication. Or you want to compare the data on two machines that are not linked with the replication. And for this, you can use the mk-table-checksum with options I listed here. So basically what it does, it logs, for example, we have like two machines, they are not master and slave, and you want to compare one table against another in these two databases. So what it will do, it will log one table, it will log another table, it will checksum them, and you will get the result compare telling if the data is the same or not. For the comparing the master and slave setups, there are such options like wait and the slave lag. Again, this is all the intrusive ways to check some data. If you use the wait option, mk-table-checksum script will look table on the master, and it will wait until the slave catches up to the same position at which master was when the locking table occurred. Then it will checksum in parallel. It will run it at parallel on the slave and on master. It will checksum the data in one table. It will checksum the data on the slave, and it will tell you the result of whether the data is the same or not. Less intrusive way, but less reliable. I mean, you may use the slave lag option, and in this case, while checksumming in parallel the slave, the master, and the slave, it will also notice the seconds behind the master value, which was on slave at this point. And if you see that some data is different, you should also look if the slave was lagging at that time. So if some rows are missing, that maybe they didn't just get to the slave yet. So this doesn't, you don't need to log the tables in this case. But again, you may need to run it several times until you get some acceptable result. But today, we mostly will be talking about the less intrusive way to do this is to use the replicate option. I will explain how it works in the next couple of slides, and a final note for these slides is that mk-table-checksum actually uses different algorithms for checksumming. We will talk about them in more detail a bit later, but here there are three main algorithms that can be used for checksumming in this script. So algorithm. The checksum actually relies on the checksum table statement, which is built in MySQL, to checksum the table. The second algorithm is actually order independent, and sometimes it's very important. For example, if the physical order of rows on your master is different from the order of rows on the slave, then some of the algorithms like accum and checksum, they will tell you that the data is different. But in fact, if you don't really care about the natural order of the rows, then you may consider that the data is the same. So if it's your case, you should be using this second algorithm. And the accum is order dependent, and it actually uses the accumulator variable. So it checksum row by row, adds this checksum to the variable, and then checksum the whole thing all over again. And it's doing it for each row. So, talking about the replicate option, what it does, it is used to check the data in master and slave setups. So basically, how it works. First of all, it creates a special table called the checksum table, or actually you can give any name you need, but for this presentation, let's use it. Let's call it like a checksum table. So it creates the table on the master, it gets replicated to the slave. The structure of the table, the main thing we need to know about this is the table has the column with the database name, the table name, the chunk number, we will go on to talk about the chunks later, and actually the checksum on the master and on the slave. So basically in one table, after the script runs, you will see the result of what table was checked, what were the results on the both machines. So how it works? Actually it's using the replace into table here is the checksum table, and it selects the data from the table it's going to check, runs it through the checksum function. It's like an abstract function. It depends on what algorithm you are using. But what happens is it runs this as a one statement, and that's very important. So it doesn't select checksums and then insert it into the table. It happens all at once. And this is very important because in this case you don't have to worry about what updates are going in parallel. I will explain it now. So what actually happens is you're running the checksum on the master. The whole process runs on the master. It generates these replaces with selects on the master. And these statements are serialized to the binary log. So you don't really care about whether there are any updates going on master at that moment, because they will be serialized in the same way the slave will receive them. So when the statement arrives on the slave, I mean the statement replace into select from the table checking, it will checksum the table on the slave with a select. So the statement arrives, right? We're speaking about the statement-based replication here. If you're using the row-based checksum, mk-table-checksum will automatically switch to the statement mode. So the statement arrives on slave, it runs on the slave, and if the data on the slave is different, it will produce different result. So that's the whole point of using the replicate option. Statements come from master, they are serialized in the binary log in the same way they are done on the slave. So slave receives them one by one. At some point it gets the checksum function, checksum statement we see here, and we can be sure that these statements reflect the same point in time on slave and on master, because like this is how replication, statement-based replication works. So we execute the statements, we don't replicate the data change itself here. So if the data is different, you can understand that by querying the checksum table on the slave after the process has finished. So after the checksum process has finished on the slave, you can query the checksum table to see what's the difference. And here's actually an example from the market documentation page. And it shows the query you need to use on the slave to see if there are some tables out of sync or some pieces of data are out of sync on slave and master. So in this case, the checksum from checksum is the checksum table we are using. So it actually compares the CRC. This is a checksum, actually, the checksum value. And it selects your database, table name, chunk, again, about chunks a bit later. Also, it compares the count of the rows in both tables. And the where statements actually shows if the count or the CRC is different, give out this result. So after the process is finished on slave and on master and on slave, you can query the checksum table and you can see if there are some pieces of data or some tables that are different on these two machines. So this was like a basic introduction into the mk-table-checksum, so how it works and how the replicate option works. So if there are any questions on how the replicate option works, let's discuss now, because everything further will be relying on this concept. Okay, great. I hope it's clear how it works. So the second part of the talk, actually the main part of this talk, will be focused on how we are building the continual replication sync strategy. So why do we ever need to worry about this? If you can run the checksum, for example, check all your tables, all your data when you need, and see the result, then why do you need to worry about the continual replication? The problem here is that checksumming doesn't come for free. It has the overhead. It adds the load on the master. If you are checksumming the MySQL tables, it will add locking because it's actually selects. Imagine like 100 million row table and the select running, getting all the data and checksumming it. This will definitely add serious overhead on your master, and you know, like huge select running in MySQL can really hurt the performance very badly. So that's why it's very important to somehow spread this load across the time. So if you have some serious database sizes or even some middle size, it may be not acceptable for you to run the checksum at that one process. You will want to spread it across the time. So before we start talking about how we build the continual replication strategy, there are some things to consider. First of all, learn about your data. I think if you're managing the database, you already know it, but again, it's never it's a good idea to double check the things. So you need to know what data sizes you have, what index sizes you have, what storage engines are used in your setup. I mean, if this MySQL be prepared that the checksum process will log the tables, and you should be aware of this. If you're using InnoDB, it's less intrusive, but again, huge selects can cause problems with InnoDB as well. And look for the tables without numeric date indexes. I will explain why this is a problem later when we're talking about the issues in the mk-table-checksum script. But this is an important point to consider as well. So, we all know, I have tried to explain the huge selects which do the checksums on the table on the whole table is sometimes not acceptable. So what's the solution? There's a great option in the mk-table-checksum script called chunk size. So basically what it does, it helps you to divide the huge select. For example, we are talking about checksumming one table, one huge table. So instead of checksumming it all at once as a one statement, you can chunk it into smaller selects. For example, you may check by 1,000 rows at a time and do it several times, just spreading the process. So instead one huge select, you will get a series of smaller selects which are faster, and they are less intrusive. On InnoDB, they will produce less overhead. And for MySQL, you will not have to, other threads will not have to wait until the huge select completes, because it will be running like one by one. So the mk-table-checksum actually tries to choose the best index to split the data into a number of chunks. So for example, if you have the integer primary key on a table, it will identify the boundaries of the table. Yes.
Is there a default value for the chunk size?
1000. Yeah.
Chunks.
Yeah, it's a default value if you use the replicate option. If you don't, again, yeah, it will checksum the whole table. So if you have the primary key index, integer primary key index on the table, what it will try to do, it will try to identify the boundaries of the table. It will get the maximum value, minimum value, and the maximum value. And it will add the where clause to the checksumming statement. So it will check only, for example, where the ID more than 100. Then next chunk will be checksum data where the ID more than 200, but less than like 300. So you will get these boundaries, this between statements in the select. So this is how it will try to divide the table in chunks. And here we come to a big problem. Only numeric and date type fields are supported for chunking right now in mk-table-checksum, because it's very easy to identify the boundaries for these data types. For the varchar, for example, it may not be as obvious as for integer. So that's why earlier I mentioned that you need to see if there are any huge tables in your setup that that don't have the numeric or date type indexes on them, because these tables may become the big bottleneck in your checksumming process. So we have divided the huge select of checksumming into several smaller chunks. But again, we are running them all at once on the production master. And yeah, this has reduced the load a bit. But again, we're chunking all the tables through all the data through the database at once. So all the data gets checked. If you have if you have a lot of data, then it may not be acceptable for you to do this. The problem is, for example, we have noticed for some clients with a lot of data, the checksumming process can't complete, for example, overnight. It can take more than 7, more than 8, more than 10 hours. So, for example, if a client tells, okay, we want to run the checksumming to know if the master is in sync and slave, but we want to do it in a maintenance window of 2 hours overnight. Then checking even selecting a better chunk size will not help you, because all the data will have to be chunked anyway. And here where the modulo and offset parameters are coming into play. Actually the modular option tells mk-table-checksum to check every nth chunk of the data. So if it's set to, for example, 3, each third chunk will be checksummed. So imagine a table, for example, let's say a table has 1,000 rows. We set the chunk size of 100, so we get 10 chunks. If we use the modulo equal 2, each second chunk will be checked during the process. So it will skip another chunks. So the modulo and the chunk size, and these two parameters can be used even in a standalone mode. For example, you have a big table, you want to quickly check if there's any data out of thing. I mean, it doesn't, you may miss some chunks, but if you have a big description in the database, big pieces of data out of thing, there's a big chance you will get over them even if you're doing each fifth chunk, for example, or every 10th chunk. So you can run quickly and see if there are any discrepancies at all. For example, before setting up the replication process, replication sync process, you may want to just to get an idea of whether the data is the same or not. The second option is offset. Offset is actually used to rotate the chunks that are checked. So the modulo checks, for example, each nth chunk. And with offset, you can control the modular value. So the offset can be controlled by script, for example, your script, or it can be a SQL expression. So here's an example. We have the module of 7, and we have an offset equals a weekday of the null function. The weekday will give you the different value each day. So if you're running the checksum script every day with these parameters, once a day, it will check all the data in 7 days. So it will, you will have all the data in your database checked in the 7 days. And each day only 1/7 of all the data is checked. So it's obvious that this approach adds much less overhead and load on your production system, because you don't have to check all the data. You can check 1/7 or 1/10 or whatever you find applicable to your situation. I forgot to tell that actually chunk size can be set up in megabytes or gigabytes. So for example, you don't want to check 1,000 of rows, but you decided to check like 10 megabytes per chunk, or like 100 megabytes per chunk. It will use the information MySQL provides about the data sizes. It's approximate, but again, you may want to use this option as well. So now we understand how to spread the checksumming process across the period of time. But we need to choose the chunk size, modular, and offset which fits your setup best. So there's no like optimal setup for every situation, because like everyone has different load on their production system. Everyone has different data volumes, and everyone has different maintenance window which you can use for the checksumming process. So the smaller chunks, of course, make the work on master work faster. So checksumming 1 million of rows and checksumming 100 of rows will take different time, obviously. But the problem here is if you choose too small chunk size, you will add more communication between slave, master, and slave. More data will be written to the binary log, and the slave will have to get more the data from the master. So you try to find the balance between the chunk size and the overhead of the network communication. I would say that the default 1000 works pretty fine for a lot of setups. So you may try to experiment and see if it improves, like increasing chunk size improves your performance or decreases the overall time the checksum process takes. But very often we really stick to the default value, and we found it's rather good for the most of the setups. So modular and offset, again, it depends on your workload. For example, in some cases, checksumming the 1/7 of data every day can even take a huge amount of time. So for a couple of clients, we have the checksum process which checks all the data in a month. So we are doing very small pieces of data every day, or even several times a day. But the whole process can take a month to checksum. So in this case, we're trying to stick to the maintenance window we can use on the production system. So for example, overnight, a couple of hours overnight. But yeah, I tell you that the continual replication process can take quite a long period of time if you have a lot of data. So before you start setting up, you can experiment how fast it takes to checksum a piece of data on your setup. So you can start with some small amount, like 1/100 of the data, or half of the data, or 1/50 of the data, or 1/10. So just see how much overhead it adds in your particular case. So, and the offset is obviously chosen to match the modular. So if you use the module of 7, you will obviously want to offset to be changed every day. if you run the checksum script once a day. So it depends. Actually, offset should be changed. So when you run the script one time with one offset, the next run should be changing offset. So you get this process flowing. So here we come to the automating the process. So we have identified what chunk size we want to use. We have identified what modular and offset we are going to use in our setup. And it's a good idea to wrap things into some scripts to automate the process. So I didn't show any examples here because really we use pretty simple scripts at Pythian. It's just a shell script which takes the parameters, sets up the chunk size, the modulo, and changes the offset each time the script is executed. So for example, for the 7th day rotation, we put the script into the cron tab, it runs every day at given time, changes the offset, and the next run will change, will checksum the another portion of data. So you can come with solution like you prefer or you like. But again, automating these things is pretty easy. Actually, I forgot to mention here that you will also want to automate the check process on the slave. So you have run the checksum script. It has checked some portion of data on both master and slaves. So it's a good idea to put some script on the slave, which will run the query I showed you before, which tells you like this table and this table they don't match each other. And actually, yeah, you may want some warning to be emailed to you when this happens. At Pythian, we run the daily check, so each day we see if some slaves get some pieces of data out of it. The idea here is you don't have to wait until all the data gets checksummed to find the problem, because when one chunk was already checksummed, it will get checksummed on slave. So you can, after the script has run once, you can already compare some data on slave and master, and you can start investigating if you see the problems already. So in the checksum table structure, as I mentioned, there's a database name, table name, and the chunk number. So basically, when you're using chunking, you will have several rows for each table in the results for each table. So we will get, for example, the chunk number 1, the checksum value on master is this, and the checksum value on slave is this. So you can easily see if some piece of data is different on master and slave. So not the all data, but only some small pieces. It makes it very easy to fix it, because like you don't have to dig into the table and find what was wrong and what fields do not match and etc. You get a pretty good focus on what particular data is out of sync. Of course, the mk-table-checksum script, it's still developing and it still has some problems which we faced when we set up on different environments. And again, the biggest problem here is that chunking is possible only on tables with numeric and date indexes. This is a big problem, because if you have a huge table, so let's say like one of the largest table in the database, and it doesn't have the numeric or date index, you will not be able to keep this smooth flow of the checksum process, because it will be a bottleneck. This table will have to checksum all at once. Like even if you have some smaller tables, this one needs to be checksummed like a single piece of data. So you may find some workarounds yourself. For example, if other tables don't depend on this logically, you may want to checksum this table maybe once a month or once couple of months, and other tables just keep chunking them and checking continually. But very often the data in such tables is important, and you need to check it more often than once a month again. So what we end up doing, like there's no workaround for this one, because like it's not so obvious how to identify the boundaries in such tables to get the good chunking. Sometimes even we have to change the schema of the database to add an index just for the purposes of the checksumming. So we add an index on such table, and we use it only for checksumming, but the table then fits into the process we are trying to build, and that's what we have done several times, I would say. In some cases, really, we end up extending, for example, the maintenance period if a client agree with this, and we do the checksumming all the tables as a single piece of data. But of course, on the very large data set, that will not work. Another problem with the mk-table-checksum, it doesn't always choose the best index for chunking, and it doesn't rely. So actually, yeah, there was a discussion that it should rely on the index which the optimizer chooses, for example, for querying, for doing the boundary query, but it doesn't always do that. I think it's trying to choose the primary key right now, in any case. Another small problem which we faced, small but rather unpleasant with the mk-table-checksum is that it between each execution of this of the mk-table-checksum, it cleans out the checksum table. So if you didn't manage to compare the data between runs of the script, after the next run it will delete all the data from the checksum table. It's a bug. It's in the back database. You see the link here. I really don't know if they have fixed it in the recent version, but the version we're using across the clients doesn't have this fixed. So we had actually to change the code a bit to avoid this. It's pretty simple. You just need to comment a couple of lines to change this. But again, this needs to be fixed, and this is a problem we faced. So we have checksum. We have set up the process. We keep the checksumming going. We have automated things, and if you're doing this for the first time, there's maybe a big surprise to you that the data is really different. So the slave is different from the master. So what you're going to do then? So you're finding the tables and the pieces of data which are different on slave and master using the checksum table and the query which I have shown you earlier. And the next thing you may want just to start investigating what actually happened. And this is actually the first thing that we are doing when we see that data is different. We need to find the source, because if you don't find the cause, what happened to cause the discrepancy, it may happen all over again. And fixing the data even at this point is not a priority. The priority is to find why things went wrong. First of all, the quick and easy check. Go to the slave's binary log and see if all the server IDs in the statements are coming from the master. It often identifies the problem where someone trying to write to the slave, and we have caught this several times in different environments. Then search for the non-deterministic queries and functions which you're using in your setup. Again, you may use the binary log to see what queries are coming or on the particular table which is different, and see if there are any functions that may produce different results on slave and master. And sometimes we notice that the discrepancies we see with mk-table-checksum are actually caused by rounding errors. So different versions of MySQL, and if they run on different platforms, they may use different approaches to the rounding. So in fact the data like is the same, but when it checksums it rounds it to some smaller value. So you get actually the different results on master and slave. It's a false negative, so actually the data is the same, but the checksumming process fails to identify this. So imagine you have identified the cause of the problem and you fixed it. And the next thing you want to do, you want actually to bring the data on master and on slave in sync. So you want it to be the same, obviously. So, for example, if your slave is missing some rows, or need some rows to be updated, for example, some fields have a different value on master than on slave, then the quick fix we use, for example, we dump actually the piece of data using the boundaries which mk-table-checksum used for chunking. We query this small piece of data on master and slave. We dump them using MySQL dump. We order this by primary key or by the key on which chunking was done. And we don't use the extended inserts, so each insert comes as one line. And there's easy to use the diff to see which roles, for example, need to go to the slave and you need to update them, or which fields need to get updated. Sometimes it's not so obvious, especially if you're using the master and slave setup for failover. You may, at some point of time, you were writing to the master, then you failed over to the slave, you wrote sometimes to the slave, then you failed back, and you screwed up when changing the replication, for example, flow back and forth. So in this case, of course, it's up to you to judge what data is the right data, and it's sometimes extremely hard to tell it. For example, if you are dealing with some, for example, placing some orders on the website, and some orders are on master, then you switch your application to the slave, and some orders get there, and then you need to find you need to be like clever enough to understand what the data is right. I mean, it's a total logical problem. I mean, it depends on the application logic. It has like nothing to do with the checksum process, because it only shows you the data is different, and it's up to you to decide like what data do you consider the right. There's another great tool in the MART-kit called mk-table-sync, which actually is used to not to checksum the data, but actually bring the data in sync on two different machines. So it actually shows you which roles need to be inserted on slave or updated on slave. So it basically does pretty much the same as you're doing manually with dump, but it's a bit automated, it's a bit more verbose, so you may want to try this one. But again, you need to be careful, because sometimes it doesn't produce the right result. So it's usually wise to run it in a verbose mode, which will just print you the statements which are going to be executed on the slave, for example, or on master, and only then execute them, because this tool provides you just an option, like get this fixed, and it's doing something in the background, and tells, okay, all done. I encourage you to avoid such approaches, because you need to control such things yourself. And of course, we have seen situations, and we face them sometimes, that it's more reasonable just to rebuild the slave, because too many data or the out of thing. This is caused, I mean, by the fact that with one small change in the slave, with the time, may grow to some really mess, because if you have queries that are depending on different tables, and it's usually the case, so it's very easy if you don't check it. If you don't check your master and slave for a long time, it's very easy to get a mess instead of good data on the slave. So sometimes we have to do this. So that's all I have about the building continual replication checksum process. So if you have any questions, comments, let's have a discussion. Yeah.
With the mk-table-checksum script, is there a way to quantify the level of discrepancies? One row different versus another row, or is it just a flat checksum?
Identify like what?
Like if you got tables that are 99% in sync versus 7% in sync.
I don't think you can tell like to check like some percent of the table. Yeah, but you can check the table you consider more important. For example, if you don't care about the log table, just don't checksum. I mean, I didn't go through all the options. mk-table-checksum has a lot more options. You can checksum only some tables, only some set of tables. So it's rather easy to configure. So yeah, if you think some tables are more important than others, then you can checksum only them.
Do you have any logic for choosing when it's better to use the, say, a chunk on a certain number of megabytes, or sometimes it's better to use a chunk on a certain number of rows?
I think in most of cases we stick to the rows, because data size which MySQL provides about the table, it's rather approximate, and it's hard to manage. For example, for the table you can always tell how much rows it has, right? The exact number. So we usually stick to the chunk size in rows. Great, great. No other questions. Congrats. Thanks everyone.